Hello, let's solve number of subsequences that satisfy the given sum condition. Very simple problem statement. You have an array of integers and a target, and you want to know how many non-empty subsequences have the sum of the minimum and the maximum elements below target. And you have to return the answer modulo 10 to the power of 9 plus 7. It's very simple if you look at the examples, right? If you look at the first example, let's maybe look at the subsequence 3, 6. That is a subsequence. It doesn't have to be contiguous. Otherwise, they would have said a subarray. So 3, 6 is a subsequence. The sum of the minimum and the maximum is 9 because the minimum is 3 and the maximum is 9. So it is a valid non-empty subsequence, and this is one of the subsequence they mentioned. And the key to solve the problem is to notice that if 3, 6 works, then 3, 3 works, 3, 5 works, and 3, 6 works as well. Why? Because in this example, nums is sorted. So if you always start at 3, if you always include 3, no matter which number you include on the right, as long as it's smaller than 6, and because it's sorted, as long as it's on the left of 6, then the sum of the minimum and the maximum will be below target because 3 plus 6 is below or equal to target. So any subsequence that contains 3, that ensures us that the minimum is 3, and that doesn't go to the right of 6, so that ensures the maximum is at most 6, will work. So we just need here to compute how many subsequences there are here that contain 3 and that don't have elements on the right side of 6. Here obviously the answer is 4, but the way they show it is by enumerating all the valid subsequences, but that would take too long. So this is why we need to use what I just explained to try and be more efficient. And so if we look at the second example and we try to apply the same logic, let's start with including these 3. The furthest we can get to the right is to this 6, because if we get to the 8, 3 plus 8 is 11, and 11 is too big above target. And so we have how many subsequences that include 3? Well, we can include or not this 3, and we can include or not this 6. So in total, this is 2 to the power of 2, because we have basically 2 degrees of freedom. So we have 4. Then let's include that one for sure. How far can we go to the right? Well, we can only go up to this 6. So we only have 1 degree of freedom. So it's another 2 to the power of 1 subsequences that satisfy the condition. Now, if we include the 6 for sure, how far can we go to the right? Well, we really can't go anywhere, because even if we didn't go to the right, 6 plus 6 is 12 above target. So that's no additional subsequences that satisfy the condition. And so we can stop here. Again, all of this works because the array is sorted, right? Otherwise, it wouldn't work. And so the answer is 4 plus 2 equals 6. If the array is not sorted, the reasoning wouldn't work, but sorting is quite cheap. Nums can have at most 10 to the power of 5 elements, so anything big O of n or big O of n log n will be fine. So we can just sort basically for free. And so if you've understood correctly, the way we're going to solve the problem is we are going to iterate over all the elements of the array, and at each iteration we'll count how many subsequences satisfy the condition, but we're only looking at subsequences that include the starting point we're iterating over, the index we're iterating over. So that's already big O of n complexity we're using, and to find the furthest to the right element such that the sum of the minimum and the maximum is below target. We can't use another big O of n loop because that would be big O of n squared, and because we have 10 to the power of 5 elements, that would just result into a time limit exceeded result. But because the array is sorted, we can just binary search our way to find this maximum element, right? Because maybe imagine I'm looking at this, I'm at 2. If I've done the addition 2 plus 4 equals 6, this is one operation, but this removes this candidate and this candidate as being the furthest to the right I can be, because I can go all the way up to 4, so obviously 3 wouldn't be the furthest I can go. So we'll just binary search our way through this array to achieve an overall big O of n log n complexity. And the reason why we're not counting anything in duplicates is because when we're iterating, for the first iteration, we are enforcing that the subsequences we count have this too. In the second iteration, we're enforcing that the subsequences have this 3 and that this 3 is the minimum element. And then we're ensuring that at the iteration after that we have this 3 and that this one is the smallest element. So we're basically ensuring we don't have this 3 and we don't have this 2. So every time we are at a index I, we are enforcing that we're not using elements I minus 1, I minus 2, etc. And we're enforcing that we're using element I. And if you think about that, you'll realize that we're not counting subsequences twice, which is very important, because if we were counting subsequences twice or 3 times, then we wouldn't have the right answer. So let's go to the code. Just initialize our modulo mode variable. We'll store the result in variable answer and we'll return it at the end. And so we said we'll iterate over nums and we'll do a binary search for all of these elements. So for start index in range length of nums, we are counting the number of valid subsequence that have nums start index and that do not have any elements from nums from 0 to start index, which ensures that we don't have any duplicates. And then we binary search to find end index the furthest to the right element such that min plus max is below target. Right, and we can only do this binary search if the array is sorted previously, right? Everything works only because the array is sorted. So we have to sort beforehand. Let's do our binary search. Left pointer, right pointer. While left is smaller than right, we'll get a mid pointer, left plus right plus 1 divided by 2. There's a billion ways to do binary search. As long as you get big O of log n complexity, doesn't matter the way you do it. And if nums start index plus nums mid is below target, well, that means that left is at least mid, which is what I was telling you about in the example. Otherwise, it means that I'm above target, so my furthest to the right element is on the left side of my search space. So right equals mid minus 1, because mid doesn't work, so I can just directly go to my mid minus 1. At this point, left is right, and I can take any elements from start index to left to form a valid subsequence. I should actually say from start index plus 1 to left to form a valid subsequence, because we're enforcing we take start index anyway. Start index is to be taken anyway. So we don't have any degrees of freedom on start index. About the bounds, so right will be length of nums minus 1, and left will be start index minus 1. And the reason why I'm not setting left at start index is because I want to differentiate the cases where at the end of my binary search, my pointer is at start index, which would mean that there's one valid subsequence, which is just a subsequence with one element. So for example, if my array is 6, 7, 12, and target is 12, then the only valid subsequence is 6, 6, right? And so start index would be 6, and the quote-unquote end index would also be 6. But if the target is 11, I don't want to have this quote-unquote end index at 0 as well. I want it to have it at -1, such that I can understand that there's nothing that's valid. So that's why I'm having this start index -1. And this will never be reached, so I'll never index in nums start index -1, because I'm doing left plus right plus 1, and left is strictly below right. So I don't have any out of bounds problems. So that's for the bounds. And so the first condition, I've just talked about it, is if left equals start indexed -1, that means nothing is valid. So I'll just continue to the next start index. I can actually break because it's sorted. If we take back our example, 6, 7, 11, if the target is 12, sorry, the target is, let's say the target is 11. Already at 6 it doesn't work because 6 plus 6 is 12. There's no point in me trying to include 7 and see how far to the right I can get, etc. Right? Because I know 7 is bigger than 6, so there's no way it'll work. That's why I can just break. And if I don't break, then I'll just add to answer something. And what is this something? It is I can take any elements from start index +1 to left not being the left index, left being the pointer of the binary search. So left is actually like the furthest to the right element. And so how many degrees of freedom do I have? Well, I have left minus start index degrees of freedom, if I'm not mistaken. Let's maybe take an example. If the array is 5, 6, 11, and the target is 11, then start index would be here. Left, which is the furthest to the right element, would be here. So how many degrees of freedom do I have? I have only 1 degree of freedom because this 5 has to be included. So this is left minus start index, because that's 1 and that's 0. 1 minus 0 is 1. So that's the correct calculation. I don't need to add 1. So the answer is 2 to the power of left minus start index, because for each of those degrees of freedom I can either take it or not take it, and I have to do everything modulus mod, right? And this function in Python can take a mod, and it adds equal mod. I need to take an extra mod operation to do an extra mod operation here, because if this is below mod and this was below mod, maybe the sum was above mod, and I wouldn't have taken it. So I need to do an extra mod operation here. And that should be it. Let's see if the test cases pass. the test cases given by the examples work. Let's see online. It passes. Great.